The loose debris scattered across the Subnautica world from various Altera vehicles tells a sad story about the fall of a spaceship into the oceans below, about fear, final moments and failure. But below these wreckages telling us about an event that took just a few minutes to occur is a broad record of millions of years of Subnautica's history, the world being uplifted above oceans, being torn apart at plate boundaries and worn down by the forces of nature. This is Volume 2 of Subnautica, the Rockumentary. Hello and welcome back to the Subnautica Rockumentary series, a series dedicated to uncovering the geology of the Subnautica world. I'm the Rockumentarist, everybody's favourite little rock muncher, and this is the second instalment in the series, covering the Sparse Reef, Grand Reef, Floating Island, Sea Treader's Path, and the Crag Fields. Now, if you haven't seen Volume 1, don't panic, this video is still watchable without having seen the first video, but please do watch that. I put a lot of effort into it, and if you like this video, you'll like that one too, promise. Now, once again, as a disclaimer, I'm a first year geology student, which means I don't know everything. I try my hardest, promise. But if you notice anything I missed or got wrong, I'm open to corrections. I do research anything I don't know much about, but I am going to miss some stuff by nature. I'd also really like to thank you for your feedback last video. It's so nice seeing such a positive response to my work, and I've used it to improve my approach to this video, so hopefully this one should be even better for you to watch. Okay, with all that out the way, let's head over to our first area, the Sparse Reef. Sparse Reef has the unique situation of sitting right next to what we could only assume is a plate boundary, being right next to the Blood Kelp Trench, an area we're going to cover in a future volume. Trenches are formed on subducting plate boundaries, where the colder, denser oceanic plate moves under the relatively warmer, less dense continental ones, which causes the rock on the plate where it is subducting to bend. This means a lot of the Sparse Reef rock has undergone lots of pressure, causing faulting, where the rock moves due to the force on it exceeding its strain. This is most likely why we have these large gaps in the Sparse Reef seabed, although these are open for other interpretations due to the very vague nature of the rock here. The actual rock itself appears to be a type of shale, however I wouldn't be surprised if this was actually more of a metamorphic slate or myelinite. This is because when faults happen, the force of the rock moving can cause the rock to change compositions, or as we call it, metamorphose. In this case, one of two things could have happened. We could have had a type of metamorphism called regional metamorphism, which is metamorphism induced by pressure, creating a slate, schist or gneiss from the shale, depending on how much pressure was actually applied. Or we could have had dynamic metamorphism, a type of metamorphism produced by shear forces from events such as faulting, that in shale can produce rocks such as myelinite. Whilst texturally this rock looks like a shale or a slate, being flaky and dark grey, if this was a shale and had undergone the degree of force required to produce these large faults, we'd most likely be looking at a medium to high grade myelinite in my opinion, with the grade describing how high the force it has undergone. Or at the very least a schist or a gneiss, with schist being the medium grade regional metamorphosed rock and gneiss being the high grade. Subnautica 2 devs, if you can hear me, more diverse rock textures, so much less hassle. Now, as the name suggests, Sparse Reef is, surprise, a reef, but not a very active one. The corals here appear dead and the water is far too cold and too murky to sustain coral life. However, hope is not lost. The fact that corals did grow here suggests this place was once in shallow waters, and with time this area should go shallow again. As one lovely commenter told me on my last video, when coral reefs form they grow on top of each other, so when this place does eventually see the sunlight again, new corals should be able to grow on top of these old ones and continue the coral record. So, Sparse Reef may not be so sparse in the future. As of right now though, if you were to drill a core into the middle of this coral, you'd likely not see some positive results. When studying corals, scientists, including paleontologists, will drill cores into the coral to look at the history of the reef, often revealing quite a few different corals and different coloured bands, which tell us about different climates. Larger, lighter bands tell us this area was warm, whilst darker bands, called stress bands, tell us the environment was undergoing an extreme climate. And for the last corals to grow here in the Sparse Reef, it's likely we'd see a high frequency in these stress bands as the conditions move away from the required conditions to sustain coral growth, before eventually the coral dies and bands stop recording. And of course, since this is a reef, there's going to be lots of fossils. It's obvious we'll have many coral fossils, since corals are made of calcite, one of the most common minerals for fossils to be made of, but we'll also find a lot of fossils related to other reef organisms, such as crinoids and bryozoans. Now, I did mention crinoids in the last volume in the Safe Shallows, but I didn't go into too much detail on them, so let's talk about crinoids and also bryozoans. Crinoids are often called sea lilies, although not every crinoid is a sea lily, and whilst most fossils you find of them consist of just their stem, made of calcite segments, in life they had a flower-like structure on top, with a calyx for a body and feathered arms, and despite looking like a plant, they're considered animals and are still alive? What? Yes, crinoids are still living, attached to the sea floor and occasionally crawling. Ooh, that's gonna be my nightmares. Let's talk about bryozoans instead. And also a living mesh of small zooids in a calcite and chitin skeleton, the humble bryozoan does not do much in life. It attached to other animals, rocks, or your fellow can of pop, and that's about it. They're commonly found in reefs due to the warm conditions, and filter feed using a mouth-like structure called a lophophore, which looks like... what is that? You know, for someone studying paleontology, the things I'm meant to enjoy looking at sure are horrifying. Okay, you know what? Back to rocks. This is too much. Yeah, the rocks. We aren't done with them quite yet. The only problem is, what are we looking at here? These massive death spike structures are everywhere along the Sparse Reef and Grand Reef especially, and they're definitely odd compared to a lot of the standard geology you'd look at on a field trip. However, I'm not completely lost in the dark on what these could be. Looking at the position of them next to the subducting plate, I'm fairly sure out of anything these could be tors. Tors occur when a magma body intrudes an overlying less resistant rock, such as a limestone, and cools as an igneous rock. Then, when the weak rock gets weathered away, you get left with a standing tower of igneous rock, such as the granite tors found in Dartmoor. It's not a perfect visual match, I'm aware, however, given its position on the map geologically, and the sheer difference between these and the lower rocks, this seems like a plausible explanation to me, although if you do have any other ideas, feel free to comment. Hopefully the diagram I drew here helps explain my reasoning a little better. This concludes the Sparse Reef geology, but we're not quite done with the reef environments. Behold, the Grand Reef. The Grand Reef is characterised not just by its large expanses of corals, but also great masses of limestones that expand a huge area on Subnautica's world. Since it covers such a vast area, there's a lot of individual features to look at in the Grand Reef, but since I don't want to be repeating myself on features I've covered before, such as the large limestone arches that can be found, I won't be discussing these in today's volume to save repetition, and you can see me cover them in the previous volume. However, there is one thing I do want to go over again, because I want to add a bit more interesting detail to the conversation surrounding them in Subnautica. I covered black smokers when talking about the dunes last volume, but due to their abundance I want to bring up another interesting point about them, which might pique the interest of any Altera Corporation staff watching this video. Due to black smokers forming from hydrothermal fluid deposits, where fluid is heated by magma then rises, and this fluid carries important metal compounds in it, around the black smoker geologically we can get metal ore deposits called volcanogenic massive sulfides, or VMS for short. These deposits contain large amounts of copper, zinc, gold, silver and lead ores, and are often found where there is a presence of igneous rocks. Now you may be wondering to yourself, but Rockumentarist, didn't you just say that these are limestones? And you'd be right. Kinda. Because underneath these limestones, as made clear from the Sparse Reef geology we discussed earlier, and looking at other places in the game, such as the magma caves, it's clear these limestones are underlain by igneous rocks, which would actually make it a feasible place for these VMS deposits to form. They're significant when it comes to our own sources of metal ores. Given how many black smokers we have in the area, the amount of ores present in our VMS deposits here could be economically viable for Alterra Corporation to mine. If they didn't, you know. Usually these VMS deposits are found in between an older and a younger igneous rock, with the older rock usually being what we would call mafic. Now, since this is likely to be a new term to most of you, let me explain what mafic means. In igneous rocks, we usually divide them by how much silica they contain. The highest silica contents in a rock are over 65%, called felsic rocks, like a granite. Then we have intermediate rocks, like andesite, which have 65 to 52% silica. Then there's mafic. These have 52 to 45% silica in them and can be rocks such as basalts, a fine-grained mafic rock, or gabbros, a coarse-grained mafic rock. Below 45% silica, it may also be worth mentioning, produces us ultramafic rocks, the rocks in our mantle, such as peridotite. But we're going to focus on mafic rocks, since these are what VMS deposits form next to. Since this mafic rock is likely situated on the oceanic plate, I have a lot of explanations for this that I'm going to cover next volume, but for now, just trust me, this is probably the oceanic plate. Then, looking at our sequence of rocks in an oceanic plate called the ophiolite sequence, this is likely going to be a basalt, the mafic rocks formed at the top of the oceanic plate. However, if we were looking at VMS deposits further down in the crust, we'd be looking at gabbros, or maybe dolerite, which is a mafic rock with intermediate-sized crystals, an in-between of basalt and gabbro. VMS deposits also typically have younger volcanics on top, and given in the dunes I speculated we'd have volcaniclastic sediments around, these may have also deposited on top of our Grand Reef, giving us our younger rock and therefore suitable conditions for a VMS deposit. To support my theory that we have underlying volcanic rocks, especially volcaniclastics, there's a fault nearby. On this one in particular, let's go into a little bit more detail. When looking at faults, we have two walls. The hanging wall, which is the side of the fault that seems to have an overhang on it, and the footwall, which is the side of the fault that seems to be the base. We also use the words down thrown for the side that has moved down relative to everything else, and up thrown for the side that's moved up. Now let's look at our fault here. We have a limestone and what looks like a volcanic rock. Sweet! The volcanic rock, as you can see, is our footwall, and the limestone is the hanging wall. And since the volcanic rock is usually invisible, and now it is visible, this means it must have been upthrown from its original position underneath the limestone. When describing faults, we usually describe them in terms of the hanging wall, so in this case, the hanging wall has been downthrown relative to everything else. Different faults have different movements of the hanging wall, and when the hanging wall moves downwards, it's called a normal fault, and is formed by tensional stresses. So this rock was pulled apart a little bit. Nice! In the opposite case, where the hanging wall is upthrown, it's called a reverse fault, and is formed by compressional stresses. Also in the Grand Reef we have blue balls! I'd make a joke about my boyfriend, but my family watches this channel. More formally named anchorpods, when I originally saw these life forms, I assumed they might contain some kind of mineral in their composition, but according to the in-game databank entry, it's a very biological life form. However, looking at the structure of the root system provided, I think these life forms may live and work in similar ways to the bryozoans I mentioned earlier, specifically a type of bryozoan called the Phenestellidae, which forms a mesh-like shape. Also similar to these roots are retiolitid graptolites, another mesh-shaped animal, although more in a 3D way that resembles what the root systems look like. Graptolites, similar to bryozoans, are animals that consist of many colonies of zooids that live in gaps in the structure called thecae. However, unlike bryozoans, which are made of calcite and chitin, graptolites are made of collagen, and due to the similarity between these anchorpod roots and the retiolitid graptolites, anchorpod roots may be composed of a similar material to collagen alongside tissue material, or the roots may have evolved in a similar way to the graptolite species, albeit for different reasons. Of course, this is definitely a stretch, but I thought it'd be interesting to mention their similarity to fossil species that contain minerals in their body. Going into the deeper cave systems of the Grand Reef, we can also see stalagmites and stalactites. I'm sure you're aware of these due to how popular they are, but I suspect a lot of you don't know how they're formed, so let me explain. Stalagmites, the ones on the floor, form when dripping water in caves deposits a mineral onto the cave floor, which then precipitates out of the water. And stalactites, the ones on the roof, form when that mineral precipitates before the water falls. These ones in particular are huge! We'd also have a rock formation called flowstone, which is where the same stuff happens but on the cave wall instead, giving the illusion of water flowing onto the cave walls in the stone. Pretty neat. Of course, I could go into the fossil record of this place too, but unfortunately it's just going to be incredibly similar to the other reef settings mentioned earlier, and this script is already getting long enough. So, let's breach water for a bit and talk about the floating island. The main geology of the floating island is characterised by mudstones, limestones and sandstones, a combination of many rocks we've already looked at previously. However, the way they're put together here is different to other places, with the limestones forming the larger hills and the sandstones and mudstones forming the lower lying rock underneath, something that is very typical to real life geology. Areas where the softer mudstones and sandstones were exposed would have eroded faster than the harder limestones, causing them to be lower down lying, and while sandstone is usually a harder rock, we can get weaker sandstones due to the sand grains being poorly cemented, or smushed for a more informal term, together, which in combination with the mudstone would make them much softer. If you live anywhere in England like me and have nearby hills, there's a very decent chance you have mudstone valleys and sandstone or limestone hills. They're kind of everywhere. On the lowermost base of the floating island, a landslide deposit has covered part of the base. Typically, landslides happen from water saturation, weathering of the rock, rocks with an unstable angle of dip, this being the angle the beds point at, and earthquakes. Which one was most likely? Well, definitely not dip. We can see the beds visibly here, and they're about as straight as people who listen to KSI's music. Earthquakes are common around subducting plate boundaries, so an earthquake could have caused this, but being surrounded by water would lessen the shock of the wave, so maybe not enough to cause a landslide without also knocking over at least one of the other bases. However, earthquakes would cause tsunamis, especially with the severity they reach at subduction zones, so saturation of the soils is possible here. Weathering is also happening too, especially areas right next to the ocean, so either one of these explanations is plausible. Now, whilst the floating islands do contain some of our more realistic geology, it also does contain a few of the more challenging features to distinguish. Underneath the floating islands we have these spiked pillars similar to stalactites or the intrusions we saw earlier, except not really, because these spikes very clearly contain distinguishable bedding planes on them, looking similar to our limestone ones, which means it can't be either of these because that tells us this was just how the rocks were laid, weirdly. I think this is the first time in the Rockumentary where I'm truly completely stumped. The closest I can find as a real-life counterpart here is the Grand Singi in Madagascar, where there's these jagged limestone pillars produced by erosion, but these usually face up. I do have a pretty crazy idea though, but be warned, this is not realistic. First, let's point out another feature. Also on the base of the floating island are these scratches which look like glacial striations. Striations are created when a moving glacier scrapes sharp pebbles across the rock it's travelling across, creating distinct scratch marks on the surface. Now, note how important the fact it's on the surface is, because these are on the underside, which means our beds could actually be upside down, something that does occur in actual geology due to tectonic forces. However, if this really were the case, these limestone stacks would be deformed beyond belief, which is why I said it isn't at all realistic. However, it's at least an idea, I suppose. This is a fictional game, so I think we can just safely put this one under the "it's a fictional alien world" category of geology, as opposed to geology that actually reflects our real world. Of course, if there is something it could be instead, do let me know, but I don't have a clue as to what could realistically be like this. So let's get on to my slightly more unrealistic and a wee bit insane theory. Another question I did have on my mind was, where did this geology come from? As you may know from my last video, I speculated that the floating islands used to be over the dunes, but this isn't their origin. Where else on the map has the closest set of geology? Well, there's the grassy plains, which has sandstones that are similar, but no interbedded mudstones as far as I could see. However, they are next to a set of limestones in the kelp forest, so it's not entirely unplausible. There's also parts of the map I haven't covered and don't know the geology of, in which case I'll update you in a future volume. Or they could be from the sub-zero part of 4546b instead. I mean, we have glacial striations on them, a feature also present on the rock in the below zero map. With similarly coloured bedrock and these similar spikes, which in below zero's case are hydrothermal vents, although a hydrothermal vent wouldn't have limestone bedding on it. But hey, maybe it wasn't intentional, it was just part of the rock texture, in which case, maybe a chunk of these vents came off and floaters attached themselves before drifting, creating the base for the floating island. And over time, this island would have gone through several environments, creating several different rock types, especially when at different sea levels we get interbedded sandstones and mudstones from sea levels rising and falling, which deposits different rocks depending on the depth of the water. And the limestone, I mean, maybe there was a time where the floating island was on its side on the seabed, explaining why limestone was only on one side of the island because it accumulated there, creating a steeper profile, and then later large floaters picked it up again, where it drifted overseas to the part of 4546b that we're situated on, creating these random island with different geology in the middle of the Grand Reef. Rockumentarist here. It is so much more plausible that was just part of the cave roof of the Grand Reef, the bottom of the bit, but it was so insane to listen back to my voice that I think I'm going to keep it in for pure comedic reasons. Yeah. Absolutely don't take that part as gospel. In fact, it was just meant to be a silly little theory. It's let's just move on. Unfortunately, our next two sections aren't going to be as interesting or theoretical. The Sea Treader's Path and the Crag Fields later on both have very boring geology in terms of rock type, only being composed of about one or two sets of rock called massifs, which is, you guessed it, just a large uniform set of rock. In the Sea Treader's Path we seem to just have a massive limestone, but underneath we have a set of mudstones that are special since they show something called desiccation cracks. These form when mud in a dry environment is exposed to the sun, causing water to leave the mud, which makes it contract, forming these polygonal shapes. So these rocks underneath were originally in a dry environment, most commonly a desert, but it's not concrete proof that it was one, because these can occur in other hot environments. All you need is mud and the sun. There is no evidence to suggest what kind of limestone the surrounding bedrock is, but the sands on top may have been carried over from the nearby dunes, or deposited at the same time. The caves here are massive, being a lot wider than the ones seen in the kelp forest, so are likely eroded for a lot longer than the kelp forest was. Caves this wide aren't just products of coastal erosion. For example, when glaciers melt, the meltwater can gush through an already existing cave, widening it further. But with no existing evidence in this area for glaciers or any other we've covered bar the floating island, this isn't likely, and since other features like arches are around, I'm still going to push with the idea of this also being a past coastal area. This cave is also very odd due to the fact it features no cave features like stalagmites or stalactites, unlike the Grand Reef, which leaves this area a bit of a mystery. Unfortunately, I wish I could tell you more about this area, but that's it. There's just limestone caves and a bit of sand and some mud. The Sea Treader's Path is a very uniform area, and it leaves not much room to talk about anything else, because the processes that form these caves I've already covered in Volume 1. So, without further ado, I'll be moving on to our last part of this volume, the Crag Fields. To people that don't know a lot about geology, the Crag Fields may look super interesting with lots going on, but as I've said before, it's all one rock. Crags just refer to steep, jagged rock formations, and in this case, it all appears to be more limestone. Often, crags are associated with mountainous areas, but not always, and are just formed from erosion. Often this shape comes from when limestones have a couple joints, and the erosion or weathering happens between the joints, leaving a point. Rinse, wash, dry, repeat. In the Crag Fields, it's likely these beds were also tilted, likely after erosion, since the crags don't necessarily point upwards and instead to the side. How do we know that these are limestone crags and not the igneous rock I mentioned in the Sparse Reef? Unlike the Sparse Reef, these crags have very flat surfaces on them that taper towards the top, meaning they likely come from beds and not intrusions. And although an intrusion happening along a bedding plane forming this shape could be plausible, due to being situated next to two limestone areas, I'm much more inclined to say that this is also a limestone. And with that being the only geology present in the Crag Fields, this concludes Volume 2 of the Subnautica Rockumentary series. I had fun making this and I really appreciate all the support you gave on Volume 1 in this series. It means a lot seeing all the comments saying I've gotten them interested in geology, and all the comments that see a future in my channel. Now that most of my uni work is out the way until year 2, hopefully I can focus a lot on making volumes 3 and 4 for you, as well as a couple other fun ideas I have planned that I'm sure you'll enjoy. Do consider subscribing if you enjoy to see geology posts on my community sections and other geology related videos. Have a lovely day, and once again, eat your rocks for extra nutrition.